regarding first topic. Do not hesitate to interrupt me or to ask to post your question in the chat during this short presentation. Okay, so basically it's a follow-up for those who were attending the meeting in last September. So it's some kind of follow-up of this ongoing work where we develop deep learning techniques based on variational formulation and weak constraint for DVAR. So here it's basically a reminder of the kind of formulation we consider to derive the variational formulation that we will plug in a deep learning framework. So it's a very quick reminder here. So basically we can start from a standard state space formulation with a representation of the dynamic here using some kind of differential equation, and we have some observation model, classic one. And in our case, in the application we consider up to now, the observation model relates to some kind of irregularly sampled observation, as illustrated here for a sea surface height mapping. And it's a standard way to state the reconstruction of a gap-free field, given the irregularly sampled observation, is a minimization of a variational cost with two terms. The first term here relates to the observation model, and the second one here relates to the dynamical prior. And you see here you have some phi operator, which is the flow operator or the integration of the differential equation. And we can rewrite this cost through this equation here with those two terms, which is some kind of matrix formulation of the previous cost. And that will be the kind of formulation we'll consider, as I would show right now. So here, the idea now is to based on this variational formulation here, is to plug this into some kind of end-to-end architecture, where the goal of this end-to-end architecture is to use as input some observation data to get as output the gap-free field. And the end-to-end architecture will mimic some kind of gradient descent for the variational cost. So what's important here is that in that case, we have a prediction of observation model, so no trainable parameters for the observation model. We'll have a trainable prior, especially the operator phi, that will be trained from data. And here we can consider different formulation. I will come back on this later on. And that's for the variational cost. And then we have also, when we plug this into the end-to-end architecture, in this architecture, we have we consider a trainable gradient-based solver. So it means that the end-to-end architecture mimic some kind of gradient descent, which is based on the gradient of the variational cost. So here we use the automatic differentiation tools embedded in differential frameworks like PyTorch to compute somehow the adjoint operator corresponding to, and then the gradient corresponding to this variational cost. So here, again, the solver can be trainable and will be trained from data, meaning that all the trainable component will rely on the definition of some learning criterion from which, and based on some data. And mostly in the following, we consider a supervised framework where we assume we have a ground truth state, so that we can basically minimize the reconstruction error for this ground truth data set. Okay, so that here it's an example where basically what you get is that from some observation recaps here an image based on the trained network and the trained variational cost and solver. You see here, you'll mimic some gradient descent here in based on the evaluation of the variational of the gradient of the variational cost And the goal here is to minimize the reconstruction error. In here you see different versions of this technique, but basically you see that all those ones achieve some kind of minimization of both the reconstruction cost based on the variation of the gradient of the variational cost. Okay, so we had first illustration of this on toy problems like Lawrence 63 and Lawrence 96. And we've moved to some application to the SSH mapping. And the considered setting, so I'll present it here, where in this setting we have, we assume in this setting that we have a coarse estimate of the SSH fields based on the altimeter data, based on some optimal interpolation. So that will be the Y bar here. And we also assume we have the altimeter data. In that case, could be the Nadir altimeter data or the some SWOT data. So we have a two component some observation, and we have the same for the state. So the state will be decomposed into a coarse scale component and a fine scale anomaly. And then to define the variational model, we have two terms. One term corresponding to the observation of the coarse component relating the coarse scale component and the OI estimate, and another one corresponding to the fine scale component relating the altimeter data minus the OI field versus the anomaly component of the state. And as previously, we have the same kind of formulation for the prior. And here we don't use an ODE-based prior, but we use another kind of prior, which is more a global prior or some kind of auto-encoded prior, because we've shown on Lawrence 63 and 96 that was better in terms of for reconstruction performance. And in our experiments, we used a learnable, trainable gradient solver based on some specific neural network architecture, which is an LSTM, but basically it's some kind of trainable gradient descent. And we optimize all the trainable components of the model. So meaning the prior here, you see the weights here, and the solver, so that we can minimize the mean square error for the SSH field and its gradient norm. So in a supervised framework. So here an illustration of what we get for some OSCC. Considering both a 4 Nadir altimeter configuration plus SWOT data. Here you have an illustration of the kind of data we have. And here in the table here, I show you the relative improvement we get with respect to optimal interpolation. So we have a gain of about 50%. So basically we are able to enhance some fine scale information, and we recover horizontal scales basically up to something like 70, 80 kilometers. And maybe here an illustration of, you have two types of solver. Here we have the fixed point solver, which was the previous version we reported in last September. And you see that using the gradient-based LSTM solver, we get a significant improvement with respect to the optimal interpolation. Okay, so basically that's where we are in terms of application to SSH mapping. Now I would like to show new applications of the same framework, and three different ones. I'll go quickly for those different applications. The first one is we would like to use the framework to learn where to sample new observation. Assume we have some observation for altimetry again, and we'd like to know if we had the possibility to sample new measurements at sea surface, where to sample those observations to improve their consumption. That's one example. Another one is assume we have some additional observation like the SST. We'd like to know whether we could extract some information from the SST to improve, again, the reconstruction of the sea surface currents or sea surface height. And the last one is the unsupervised calibration of SWOT data. So basically, in SWOT data, you have some error due to the sensor attitude or different types of errors, and so that the before using the SWOT data, you have to separate the true geophysical signal from the from some error, and in the same way there's some development within the PhD of Quentin regarding using the 4D VAR-NN framework to achieve SWOT calibration, SWOT data calibration here in some unsupervised way. So the basic idea here is that compared to what I presented before, is to consider a trainable observation model. So before we had just some identity model for the observation. So for those different cases, we change this, and we'll, for example, for the sparse sampling, the optimal sampling learning would like to address. The idea is to consider a new observation operator where we have this H operator, which is a sampling operator, meaning that most of the output of this operator would be zero values. Only a few ones will be non-zero, corresponding to the points where you'd like to sample. And interestingly, this operator can be conditioned by some covariable. Could be like, for example, the some coarse estimate or the SST or something else. That's for the sparse sampling operator. And in the multimodal observation case, for example, the idea is to add a new term, which is this one here, where the idea is that you'd like to extract from some information from the from your new observation, the SST, Z here, that should match some features of the SSH, which is X here. And for some SWOT calibration, that's the same. You'd like to learn the operator so that from the observation you can remove the noise of the error here. So all those examples relate to add some trainable component in the observation model. The good news is that you can directly, as soon as you have some parameterization of this observation model, observation operator, you can directly plug this into the variational framework I've presented before, and you can learn all the parameters using this same kind of learning techniques. Only for basically for the multimodal setting, just the same, and for the sparse sampling case, we add some sparsity constraint to constrain operator H to be sparse, but basically we use the same kind of optimizer for the learning. So here, some very first results for this. First, for the optimal sampling case. So here, the situation we consider is that we have the basically some observation, which are the some nadir altimeter data, and we have the sea surface height from optimal interpolation, and we'd like to know where to sample new altimeter data, assuming we have some ways to measure this, and where to put these measurements to improve the reconstruction of the sea surface current. And here you have the kind of reconstruction you get compared to this. And here you have the points where we had the observation. So basically the network here learns to sample new data corresponding to the areas in the field corresponding to the greatest gradient. What's interesting here that we do not force to do this. Basically, it's learned from data directly. Another example, the example for multimodal learning. So here, the situation that we learn what we could extract from the SST to improve again the reconstruction. And basically here we have some additional gain, including in the SWOT plus nadir case study, we gain like 10%. Probably more interestingly, we gain more when we use, instead of using both SWOT and nadir data, we just consider nadir data. In that case, we have a more significant improvement using SST. Obviously, it's only for one region here, which is the Gulf region. That should be we should consider future work for investigating whether or not this applies to other regions. So basically, the key message here are with respect to what I've shown in last September, is now we can learn jointly the priors, so the dynamical prior, some component of the observation models and the solver. Especially, we can consider both optimal sampling, learn some kind of optimal sampling strategy. We can move to some kind of multimodal data assimilation without some strong specification of a relationship between different parameters. And we mainly have investigated application to SSH mapping, but basically the framework is very generic. We apply to all the case studies. So a recap here, again, so in this framework, we have 3 components, and here it's basically the status of what we've done currently regarding what are the trainable or type of observation model we've considered, the type of trainable prior, that we have some trainable solver, which is based on the iterant or the gradient of the variational cost. And all this is optimized with respect to some training costs like the reconstruction area. Probably here I mentioned a number of possible directions for future work. So we could first consider different case studies. Today, we'll mainly discuss how to probably embed stochasticity and uncertainty in this framework. That would be the discussion led by Said. There is some ongoing work within the PhD of Nicolas Lafont to deal with extremes in this. And there is some work also. Something that would be interesting is to look whether or not we could use this kind of framework to for the reconstruction of some states which are not directly observable, like for example vertical velocities when considering sea surface dynamics, which is not the case up to now. And I mentioned here a number of options we could consider in future work. Okay, that could be we may discuss this those points, and maybe here some status and what we plan to do regarding SSH mapping. So basically, what I've shown here is that we have some first demonstration for one OCC within a Gulf Stream region, for which we have significant improvement with respect to OI. There is some ongoing benchmarking experiments, and Quentin will come back on this later on, including the design of a data challenge and a number of planned developments, including with respect to Melody, including moving to a larger scale, like an ocean basin scale, like for example the North Atlantic. And another important issue is to move from OSSEs to real observation data. And probably the point here is probably to consider the kind of learning strategy you could consider for this. Okay, here are just some references for this, and that's basically what I wanted to present, so that we have like some time for discussion. Okay, so we may start the discussion phase. I've probably been slightly quick on this. Okay, there was a question of Ananda regarding comparison. So maybe Ananda, if you'd like to comment. I know you should leave at probably 10:30, so I don't know if you're still here.
Yeah. Hi, yes, I have to leave in 2 minutes. But a very nice talk, thank you. And well, I found that this optimal sampling that you proposed for the orbits of the satellite could be also applied for the design of cruises, and this is something that really has a lot of potential. But then my question also was about if you always compare to optimal interpolation, but have you done any comparison with DIVA, which is also a variational technique that is used quite a lot in oceanography for interpolation and reconstruction of geophysical fields.
No, we've compared to there is some starting comparison with a variational assimilation developed by MEOM. But it's probably comparable, or we may have slight improvement. That should be confirmed. That will be interesting to compare with DIVA. And the point here is probably that we want to distribute a data challenge with all the data and the evaluation framework to make easier the comparison. So Quentin will present this. And yeah, and the idea on this is what I mentioned here, or here, yeah, here. We'd like to distribute this or propose this within the SWOT science team working group on data assimilation and inversion issues.
Yeah, so that we can test other methods. Okay. Yeah. Thank you. So I have to leave, but it was very nice.
Okay, thanks, Ananda. See you. Bye. François, you'd like to comment, or?
There was also a question from Duong, maybe.
No, okay. It's the maybe in my results here. Where it is. Okay, Duong. The results are better when using SWOT. What? Okay, it's probably here. So here, what it's the relative improvement with respect to OI. Okay, so the greater the better. So here, basically, it's what we have for using SWOT, and what you have just called SWOT plus Nadia altimeter data, and here using only Nadia altimeter data. Is that clear? Okay, François?
Yeah, if you can go back to the slide where you present the operator. Yes. So basically, you just add this. Yeah, it was this slide.
Yeah. No, sorry. Yeah.
H of Z. Yeah. So basically, what do you do? Do you just add H in your neural network architecture, or do you use any features from the data to get H? How does it work?
Okay, here I may consider both options, but probably the most interesting one is where H is conditioned by some covariable Z. So in my example, I use as covariable Z the optimal interpolation. So let's say some coarse estimate of the field. So I assume we have some previous knowledge, some kind of knowledge, but a coarse one. But you could consider any covariate. And so the idea is to learn or to extract some features from this variable to learn where to sample or to predict where to sample. So it's not only, so basically here H is a neural network. It uses as input some variable, and the output is a matrix, which is sparse. So that also applies to the case where the input is just a constant, so meaning you have no true variable, and then it only depends on the position to learn some spatial prior for sampling.
Okay, so basically H extracts some, well, the neural network used for H extracts some features and then estimate a matrix based on that.
Yeah, and here, if you look at this, it seems that basically what's done here is to some kind of computation of a gradient and thresholding to predict where to sample, which is probably what we expect.
Yes.
But it's a way to check that the best if you minimize the mean square error, the best points to sample are the points with the highest gradient values. But what could be interesting if we change the performance, the training loss or the performance metrics. So instead of considering the mean square error, we change to something else. We may adapt the sampling, shall adapt to this. So that would be probably interesting to look if the sampling changes depending on the kind of performance metrics you consider.
And you could have a loop on the final reconstruction, maybe instead of using Z.
And then loop, yeah, you could, yeah, you could probably try to have something which would be dynamical. Yeah, probably. Yeah, could be done too. One case study that could be of interest is instead of considering interpolation like here or reconstruction, we could apply the same thing for short-term forecasting. So meaning that here that in the framework I've presented, you assume that the observed data only refer to the current day and the past, and then all the future corresponding to missing data. Then you can directly apply the framework I've presented, and then the idea would be to learn where to sample measurements to get the best prediction in the short term, on the short term. I think that could be an interesting case study too.
Okay, thanks. Thanks.
I think Redouane answered to your question. I don't know, but you may comment this if you'd like to.
Yes, actually, you did partially answer my question. It was about the loss function, because I wasn't a bit surprised because here it acts like an oceanic front detector. So yeah, fronts contribute much to the MSE. So maybe checking other loss functions would be very interesting.
Yeah, I agree on this. But yeah, it's probably not surprising. So, but it's not obvious either that it was the best strategy for sampling. But it seems reasonable at least. So I don't think we can have a theoretical, or maybe decomposing, or maybe yes, we could, because we could decompose the error corresponding to the different as a level set integrals probably regarding the related to the gradient neuron. So maybe that, yeah, moving to other performance metrics will be interesting here. Yikun, you would like to?
Sorry, I came in the middle and I saw that your slide saying that you can learn the observation model. So I thought that you were learning the observation model for the latent variable, but then I find it's not. So maybe it's a irrelevant question. Sorry.
Oh, I mean you're or maybe it's here.
Yeah, I think I was here.
Or here. Yeah, here you see that. So X is the latent variable.
Oh, X is latent variable. Okay.
But here, the way we implement this, X is the state this is the geophysical state we'd like to recover, or some kind of representation of the geophysical state. And
I was okay.
So, for example,
sure.
maybe
sorry,
for example, in the application to SSH mapping, sorry, it was here. Yeah, here. That's the way we state the state. So we have a coarse component and a fine scale anomaly. So we have some kind of multi-scale decomposition for the geophysical state. Okay. And what we learn here, we can learn we can learn some operator up to now. So we can try to learn linear or non-linear operator, but in our experiments, we got the best results using only linear operator. So I don't know here if it's something related to the
yes, I was
the fact that it's better, it's easier to achieve the inversion if you use a linear observation operator. But we, theoretically speaking, we could consider a linear or non-linear operator.
Okay, I was associating this with your past work with Said. Basically, you have you construct latent variables in the dynamics, and in that case, your latent variable is not clear whether your latent variable is a small scales or something else. So in that case, can you know the observation operator? Or?
Yeah, we've tried one version which is very similar to Said for short-term forecasting, where in X we have here X would be X here would be two components. Let's say X, the geophysical variable we'd like to consider, and some augmented component in the same way as Said did for forecasting.
So in this case, you don't know what they is.
Yeah, but
okay.
Here the G operator, basically the observation operator will only depend on this component in the same way as Said did again for.
Okay, so I was wondering if you can construct something that is actually dependent on Z.
You could also. So I haven't tried that. It won't. I mean, it's possible. Yeah. I don't think it. Yeah, it would work. But we haven't tried. But it could be tried.
I'm just curious. Okay, thank you.
Okay, thanks.
Thank you.
Okay, I don't know if there are other questions, or we may move to keep on schedule. We may move to Emmanuel. Okay, I need probably to start. Okay, so now Emmanuel, you should be able to share, I think. Okay, good, perfect.
You see that?
Yeah.
Let me try to. Okay, so what I'm presenting here is the essentially the work by Florian. Okay, for his PhD, and what I'm focusing on today is the mapping of SSH, but in the perspective of SWOT. So in presence of wait, I don't see my. Sorry, I don't see my mouse when I'm. Okay, so sorry for that. I don't see my my mouse, so I cannot show on the slide. But I think let's try. I think I don't need to show explicitly with the mouse. So we are focusing on the mapping of SSH from SWOT and Nadir altimetry, and in the presence of internal tide signal here. And so these are the recent advances made by Florian. I cannot. Je suis bloqué là. Okay. So first, a little bit of context for those who are not necessarily familiar with this. So the
Emmanuel, do you? I have no slides shared on my screen. I think you stopped sharing.
Ouais, excuse-moi, j'ai un petit souci. Là, je sais pas pourquoi quand je partage, j'ai plus la main, j'arrive pas à passer les slides. Alors je vais essayer de relancer là.
Ok. C'est pareil pour tout le monde, j'imagine. Juste pour.
Oui, on n'a plus les transparents.
Ah ouais, okay. Alors là, vous devez la voir.
Okay. C'est bon.
Et là.
Sinon, reste en.
Ouais, je vais rester comme ça, vous voyez là.
Ouais.
Okay, so a little bit of context. We are interested in the mapping SSH. So basically, the illustration here is on the top panel. You see nadir altimeters tracks, and at the bottom panels, what we want to do with a mapping technique. So basically, obtain a gridded map of SSH from nadir altimetry. And nadir altimetry here allows the study of the mesoscale surface processes, meaning that the mesoscale processes are met essentially beyond 100 kilometers. And so here we can have a good estimation of the upper ocean surface circulation dynamics through the geostrophy. So basically, geostrophy is allows you to get the surface currents from SSH. And in the perspective of SWOT, so SWOT will be a very different observation, because it will be two-dimensional. It will provide images of SSH instead of tracks, and with a much higher pixel resolution than nadir altimetry. And at these scales, we will have access to a part of the sub-mesoscale dynamics, but also to another type of dynamics related to waves, gravity waves. So to understand it, we have to know that the SSH signal, in the SSH signal, we have different components. The first one is due to the barotropic tide. So basically, the barotropic tide is the tide that everybody knows, and in practice, it's predictable. It's easy to remove from the observation, from the raw observation at the beginning of the data processing, and in practice, this part is removed from the observations at the beginning. So we don't pay attention to these components. The second component is the balance motions. These motions are those that are now estimated through by nadir altimetry at the mesoscales. And the last one is the internal tide signal, and this internal tide signal is due to the interference between the barotropic tides with bathymetry. This creates gravity waves within the ocean, at the interior of the ocean, with amplitudes that can reach hundreds of meters. And these internal gravity waves have a signature at the surface that can reach several centimeters. So basically the same orders of magnitude as the balance motions. And so in the context of SWOT, with this high resolution observation, we will face the problem of separate the balance motions and the internal tide signal, because for several applications, this separation is required. So the balance motions and the internal tide signal, internal tides have very different, have common space scales that will be observed by SWOT, but different time scales. And the first one is slow compared with the internal tide that is much faster and propagative. Going deeper into these internal tides, we can distinguish between the coherent internal tide, which is where the frequency is the same as the astronomical forcing that is at the origin of the tide, and the incoherent internal tide, that is the results of the modulation of the internal tide with the balance dynamics, and in particular the stratifications and the variations of stratification due in particular to the balance dynamics. Okay, so the first part, the coherent internal tide, can be addressed with Nadir altimetry to some extent, but the incoherent part cannot. And we wonder whether it is possible to address this with SWOT. So I'm going to talk about first the dynamical mapping of surface signature of internal tides from SSH observations, and I'm going to present I'm going to show what we do for that, the 4D-var. And then in the second part, I will show some results about the coupling of this dynamical mapping of internal tides with the mapping of the balance motions. Okay, what we use to map the internal tide is a 4D-var and with a shallow water model, a linearized shallow water model. So this is a physical model, and this physical model is well designed to represent this type of propagating motions, okay, waves, gravity waves. And so this is why we use these equations with some boundary conditions. So the equations are here on the left. The prognostic variables are UNV, velocity, and eta, the surface elevation. And HE here is an equivalent depth that is related somehow to, in the real world, it is related to the stratification in the ocean. On the right, you see a set of boundary conditions. What's important to be aware of here is that in this internal tide problem, basically the waves that are within the domain, here we have a regional domain. What's happening within the domain is essentially driven by the boundaries. Okay, what the waves are due to what is coming into the domain from the boundaries. So these boundaries are important, and I want to stress in particular the second line, where we prescribe the boundary condition for the elevation. Okay, and this boundary condition is given with a frequency here, which is the frequency of the tide that we are looking for. In the next step, we are addressing only one type of one frequency of tide. And so since the dynamics is driven by the boundaries, and at the boundaries are prescribed with parameters, we can state the forward problem here as x equal to m of p being some parameters, and x being the state vector that will be observed by SWOT. And p here gathers he, and the coefficient, the amplitude of the boundary conditions for eta. So this is an animation illustrating the propagation of a wave where at the southern boundary, the condition here at the bottom left is imposed, and the wave here is affected by he, and he is on the top left. So to solve the inverse problem, we use the 4D-var again, and where the cost function is written here with a misfit from the observation, and we also had a prior term which is not written here. So and so the parameters, if I come back to here, the parameters are the amplitude of the eta eta at the boundaries and HE. To reduce the size of the problem, we decompose. We write the boundary condition for eta as a superposition of Gaussian functions in time and the dimension of the boundary. Okay, and so instead of having an amplitude of eta amplitude at each grid point of the domain, we have only the a few parameters of the Gaussian that are used to decompose this the control parameters. Okay, so this is a way to reduce the size of the inverse problem, knowing that the domain is quite can be considered as a high dimension. And for HE, we do the same, but with a 3-dimensional Gaussian instead of 2-dimensional, because it's a field. And so this is an example, an illustration of a boundary condition for eta. So this is the only for the Gaussian function on the left side of the domain, here in space, and at the bottom in time. And so it's not a movie, sorry, it's an image. So you see that at 5 days before the mean of the Gaussian in time, you start to have the signal propagating in the domain, and then it becomes maximal at the mean time, and you still have some signal 10 days afterwards, and the entering signal is maximum here at where the Gaussian is maximal, and is 0 elsewhere, far from the Gaussian. Okay. So we run experiments using as real data and observations the simulations from Aurélien Pontet with ROMs. So in these simulations, balance dynamics are simulated with ROMs, and a wave is introduced from the southern boundary and is pulsating toward the north. So, and at some point in the middle of the domain, the waves are going to interact with the balanced motions, and will become incoherent. So here you see on the left, you see the total signal in SSH. In the middle, only the balanced motion, and on the right, the wave motions due to internal tides. Okay, so we see that the wave is coherent before meeting the turbulent part of the balanced motions, and then it becomes incoherent. And so the goal here is to separate these two, balanced motions and internal tides. So here the observations come every 3 days and 3 hours. Okay, the time window for the 4D VAR is 2 months, and I'm going to show here the 2 scenarios. The best case scenario is where we have the observation of the IT component, which is obviously not realistic, and the worst case scenario where we have the observation contains both the balanced motion and the IT components. Okay, and the matrix or RMSE and the score that is between when it's 1, it is perfect, basically. Okay, so this is a movie of the results. So if you look at the bottom panel, for example, for SSH, on the left it is the true IT signal in SSH. In the middle, it is what is reconstructed from the observation of the SSH IT only. And on the right here, it is the reconstruction from the observation of that gathers together the balance motions and the IT motions. Okay, so we see here the RMSE evolving in time. And basically, this is going to provide us boundaries. We know that we cannot do when we come to estimate both components at the same time. We cannot do better than the best here for the IT motions, and we hopefully do much better than the worst case scenario here in orange. Okay, summary, worst case scenario, 45% of reconstruction based on the scores, and base case, 85%. Okay, and the difference here is obviously due to the presence of balance motions that interfere with the reconstruction of IT motions. So in the next step, we are coupling this with a data assimilation method that we developed to reconstruct the balance motions. Okay, this is called BFN QG. QG for quasi-geostrophic, because the model here is a quasi-geostrophic model, a 1.5 layer quasi-geostrophic model. And I'm not going to enter into many details here. It has been the topic of the publication in last year. So basically, what we show here in this picture is on the left here. It is the nature run, and here is the nature run. So basically, these are snapshots from the realistic simulation, the NATL 60 simulation for SSH. Velocity and geostrophic vorticity. And in the middle panel, it is the results from the DUAX. So here I didn't say that, sorry, but the data are SWOT and Nadir altimetry simulated from the nature run. So the DUAX algorithm is on the middle, and the method BFNQG is on the right. And we found that the BFNQG method is better than DUAX to some extent, in particular for the small scales and vorticity. And the data set that has been used for this paper and is available through a data challenge that we have set up last year, and that is available at this URL. So BFN, to introduce it, basically is the poor man's assimilation method. When you have a model written like dx dt equal to qg, the forward nudging is, so this is actually, nudging is the poor man's assimilation method. It consists in introducing a term that creates a feedback toward the observation within the prognostic equation. And BFN is back and forth nudging, so it consists in applying the nudging not only in a forward mode but also in a backward mode within a time interval until convergence. Okay, so I'm not entering the details of why we have chosen this method, but there are good reasons for this. And right now for the balance motion, we are also developing 4D bar to replace the BFN. So we have coupled the two approach, the assimilation with the shallow water for the waves and the QG model for the balanced motions using an alternating minimization method. So basically, this is how it works. Starting from the observations that contain both signals, BM and IT, we first assimilate these observations into the QG model to sort of filter out a part of the waves, and the results of this is taken here, is removed from the observation. So here we should remove a part of the BMs, and the resulting observation here is assimilated into the shallow water model to get an estimation of the waves, of the IT waves. Okay, and the result of this is then removed from the observations. So the observations should reflect the balanced motions better than the previous ones, and they are assimilated into the QG, etc. After a few iterations, we converge toward the separation of the two dynamics. Okay, so it converges after a few iterations. Okay, and so what you see here is at the top panel, you see the BMs at different iterations, so the results from the QG model. So this is the truth we want to reconstruct, and the SSH at the different iterations. And you see that at iteration 10, we reconstruct reasonably well the truth. Here you see the scores, and remember the scores depending on the iteration. So the blue is the first iteration, the red is the last one. So we improve the score with the iterations. And here at the bottom panel, you see the same for the internal ties with the truth here on the left, and the results for the various iterations that are improving with the iterations. And at the very bottom part, in the very bottom panel, you see the best case scenario that we saw before, the worst case scenario in gray, and the different iterations with the thin lines. And iteration 10 is the red line, and it's very close to the best case scenario, contrary to the first iterations, or even the iteration 4 here, that are closer to the worst case scenario. A specific focus is on the incoherent part of the IT field, and to check whether the method is able to reconstruct this incoherent part, we compare these results with an harmonic analysis. So we replace this block with an harmonic analysis. So basically, an harmonic analysis is perfect to extract the coherent part, but is not appropriate for the incoherent part. And what we see here on the graph is that when it's blue, we do better, and when it's red, we do worse. So basically, we do better in the northern part of the domain, where the IT signal is incoherent, and we do slightly worse than harmonic analysis in the southern part, which is normal, I would say, where because the signal is coherent. Okay, these now I'm coming to the conclusion. So we have developed the 4D VAR with the shallow water model to estimate the internal tide surface motions from SSH observations. We have tested it. We have coupled it with another assimilation approach specific to the balance, to the reconstruction of the balanced motions. Okay, we coupled the two, and to some point we are able to reconstruct to separate the two signals and to reconstruct the incoherent signature of ITs. The short-term perspective, we want to replace BFN with 4D bar, so we are presently working at this. We want to move to more realistic setups, and this is also ongoing works. And at the longer term, it would be perhaps appropriate to add source terms, because here the waves are coming from the boundaries only, but they can be generated within the domain. It is not taken into account here. We might, at some point, it can be necessary to introduce interactions between the two models. So in particular in the IT model, to introduce some interactions of the balanced motions. And okay, and there are other applications behind that. Okay, so I'm stopping here. I think I'm done and I'm late. Sorry.
Thanks a lot, Emmanuel, for this presentation. I don't know if someone would like to start the discussion. Maybe one on my side regarding, like you have in the best case, you go up to 80 or 85%, something like this. So there's a missing like 15 to 20%. So this error, is there some limitation of the shallow water model here, or the interaction between IT and balance motion, to explain the fact that you do not go up to like I don't know, 99 or
so in the best case, there are no balance motions, so they are not involved in this. It is partly due to the fact that indeed it is a shallow water model and it does not represent exactly the dynamics of ROMs. And it is partly due to the fact that the observations come every 3 days and 3 hours. Okay, we don't. So I didn't go into these details, but the observation, a full snapshot, but every 3 days, more than 3 days. Okay, so it's probably due to that also.
Okay, so yeah, okay. So here you assume okay, the sampling lies something that is, so it's not daily.
It's not daily. Here it's 3 days and 3 hours. We have made some sensitivity experiments to test the time sampling, and but I haven't presented this here. It was not absolutely essential to me.
Okay, was there a reason for considering 3 days rather than 1 or 7, or?
Not really, except the fact that well, the point is to take a observation frequency that is not a sorry, even in French I don't find my words.
It depends on the frequency of the wave.
It's not a multiple. It should not be a multiple of the wave frequency.
Okay.
To avoid aliasing.
Okay.
So here the frequency of the wave is 12 hours, and we showed that with an observation every 3 days, for example, the reconstruction is very bad because there is some aliasing.
Okay. And if you decrease the sampling, would you expect to keep the same performance if you go to a week or 10 days?
Yes. Oh, it's worse sampling, you'd say
yeah.
5 or 6
Something
days
closer
instead of
to
3?
SWOT.
We haven't, or I don't remember, we have we haven't tried that. We haven't tried that. Or simply because in such a domain like this, in mid latitudes, the SWOT frequency will not be 10 days. It will be like if you have a gap of 5 days, it's close to a maximum, because you have tracks. Even if the track is not the same, you can have different tracks crossing the domain, going upward, downwards. Okay, so we kind of count on that.
Okay, thanks. Are there other comments or questions for Emmanuel?
Perhaps any comment on what the machine learning piece could bring to this? How would you see that?
Yeah, we discussed this a bit with Quentin and Julien. I mean, we could try to basically what I've presented before. You could try to have the X decompose as the IT and BM components, assuming probably you would have to set some priors, the operator phi, specifically for each component, or some you may consider also joint versions. And so it seems possible, or that's one option. Basically, I think there are two options. One, like basically the same kind of configuration you considered, like two models, one for BM, one for IT, and you alternate between the two. And you could probably try to set up a global formulation directly. I don't know if that makes sense to you.
Not in the details. That here, even if the models are different, in this coupling, the formulation is global already.
Yeah. But the way you solve for this is you alternate.
Yes,
so
we use an alternate minimization. Yeah.
So you could consider this in terms of networks. It means that you have like two networks, global networks, and you change iteratively the inputs for each of the network.
Mm-hmm.
And you could probably build like an end-to-end, a global network with those two networks inside of it. That would be one option. Another option would be just to set a global model and change the parameterization of the observation model and the operator phi in what I've presented. And the operator phi could be based on the QG or shallow water too. So it could be parameterized from those models, or you could try to learn from data. But that would seem feasible, I would say.
Mm-hmm.
The question is maybe more the size of the training data set you could consider, and the fact that you have enough data for supervised learning.
Mm.
But if the answer to this is yes, then I would expect this to be feasible as an application. So that could be one of the discussion. I mean, we as I said before, we discussed this a bit with Julien and Quentin and Clément, probably as the next step, one of the possible next steps in the PhD of Quentin. So yeah, probably to be discussed at some point.
Yeah.
Okay, thanks. Then we may move to Quentin for a presentation of the data challenge framework prepared on our side.
Okay. So let me share my screen. So I had some issues with my Wi-Fi. Can you hear me well? Yeah.
Yes.
Okay, great. So the data challenges, the two previous presentations talked about the data challenges that made available their data with the experimental setup in order to be able to compare different, like mostly SSH mapping methods. Yes, so the idea is to compare different methods. So what? So I think the data challenge was already presented during the last Melody session. So what has been done was to make available the data and describe the periods that were used for evaluating the metrics and the others that were used to train the models. And what we have done since is to put in place some tooling in order to automatically, like say, systematically submit some new results, compute homogeneous results in order to facilitate the comparison of methods from different person who want to submit the results of their methods. So I will first present rapidly how the workflow works, then maybe just show you how it looks like on GitHub, and that's it. So the idea is on GitHub, one person who wants to test his new method can find the data and the experimental setup. So then he can recover the data, train his model, make the prediction. And one problem we wanted to solve was how to be sure that you compute the same metrics and that you can compare that the results you have are comparable to the one that can be found on the repo. And so for this, what we propose is that the user want to submit his results, like find the data format on which he should submit the results on the repo. He uploads the prediction on some public storage, and then on the repo, he submits a file that will specify where to find the prediction data, some description of the experimental setup, a link to the code that allowed to generate this data, and then it's GitHub that will automatically compute the metrics. So it will download the submission data, compute the metrics, compare it with other results that are submitted on the data challenge, and then make a report. So maybe I will just show you what it looks like. So this is the repository on which we can submit the data. So as we say, there is some introduction about the SSH mapping task. We can have link to the training data, etc. Different evaluation setups are presented. Here we have the submission results that were computed following some results. And here we have how to submit new results. So this is the tools that we put in place. So we can have some example netCDF that we can look like to be sure that the data will be able to be computed and that metrics will be computed on it. We make it publicly accessible. And then we just add one file like this on the repo, saying where is the data, where is the code to to compute what is the code that computed this data, and then by proposing this new data on this repository, the GitHub will automatically compute the metrics and make a report like this that we can integrate in the data challenge as more results come in. So this is the tool that we put in place in order to facilitate the automatic, let's say, metric computation of the results. But the work is not done yet. What we noticed is that we still need to consolidate a bit the different experimental setups. So depending on the metrics we can have on the experiment, we can have different domains on which we want to evaluate the method, or different periods. And it's still a bit awkward to submit a result on this period or on this domain. So we mostly need to do this. And that's it for me. So the idea is, maybe if you're interested to use this, to submit some method to this data challenge, I would be interested to know how it feels, if it's easy or not, or if you want to integrate something like this on your data challenge to facilitate people that are exterior to your teams to submit some data. I would also be interested in helping you do that. That's it for me. Any questions?
Thanks, Quentin. There's one from Julien. I'll let you.
Yes. Sorry, just looking at the chat.
Or
yes, yeah. Exactly. It's GitHub Actions that so you include the metrics. So GitHub Actions is the continuous integration of GitHub.
Yeah. So just asking. So you don't like you don't use the actual code that is provided for recomputing the prediction. You only use the actual prediction for computing the metrics. Is that correct?
Yes, that is correct. So this indeed, it would be maybe cleaner. In an ideal world, I think it would be better to recompute the actual predictions, but it felt more complicated to implement, because then you need to depend on the environment of the user, like what Python package he uses, and yeah, mostly this actually. And also it would take more time. So if you have some issue, then it could, yeah. So it felt more difficult to implement, but it's true that it would be a better way.
I think that's the right approach, and as long as you're also requesting the code, that's good. I'm just wondering whether you have roughly estimated the sort of compute resources you would need, and whether the free plans for GitHub Actions would fit your need, or whether you need to go for a paid plan.
So I think we have like 1,000 minutes a month that are free right now to download some data and to compute. It's maybe 10 minutes, like if you have a 4, 5, 10 submission. So right now we can handle up to 300 submissions a month. So I think for the scale of our data challenge right now, it's okay. Another option with GitHub Actions, if we don't want to pay and we still want to scale, we can actually use on-premise workers. So we can have one computer in our lab that do the computations, and then it's free forever.
Okay, thanks, Quentin. I don't know if there are other comments or questions. Yeah, go ahead, Edouard.
Yeah, it's a simple question. I mean, do you limit the number of submissions per user per day? I think maybe it's a bit complicated to do it in this case. I don't know. I'm not very familiar with the GitHub Actions, because that's actually one advantage of using data challenge platforms. Yeah, to not let users like abuse the use of computing power, and let them, limit them with some fixed number of submissions per day. I don't know what do you feel about this?
So my feeling about this, it's really a feeling, is that right now it's not really our main concern. Our first concern is to make it easy for people to use before restricting them to use it too much. I feel like if we want to put in some restriction later, so I don't know how to do it, but I don't think it will be a big problem. But I think the first challenge is to like make it the most fluid possible, to just put it some data, get the results, and being able to compare your results with other people.
Yeah,
So,
yeah, I'm in line with this, and probably moving to a data challenge platform would be a good choice, but then people will have to register on this platform. So we thought that it might be easier just to have a GitHub for this, than so probably a different organization. And probably, so that's one. So we discussed this a bit with Julien and Emmanuel. I think we need to consolidate the evaluation periods or the evaluation experiments we'd like to consider here. Especially even the experiments which are used currently are not fully satisfying, I would say, from a machine learning perspective. So one point here is that for the experience I've reported in my presentation, which is basically the table in black here in the slides of Quentin, we use one test period, which is a 20-day period of time, and the remaining period, except 10 days before and after, as the training data. It would be better to have like a validation period and a test period, and the remaining data to be used as training data, and to have a comprehensive evaluation of learning algorithms. It would be good to define explicitly different periods of time for the evaluation. So I think we have to discuss this and to agree on this setting to propose and distribute this challenge within the especially within the SWOT science team and the associated working group. So I think that could be part or should be part of what could be produced at the level of Melody and discussed. One point on this is, okay, here basically we have only the result from our side. I know that with Florian, we have some results, but not necessary for all the periods of time we'll consider. So it would be interesting to have this, and that relates to a question by Ananda. I don't know if Renio is still here. I think, but I'm not sure. But I think your Eugenio is a student with Ananda, right? That's you working in Diva. Is it you or?
Yeah. Can you hear me?
Yeah.
Okay. Yeah. Actually, we are working with Diva, and yeah, we are. The basic cost function of Diva is actually just a smoothing term and a deviation from the observation, the MSD. But we have been modifying a little bit the cost function, adding a term that is somehow adding a multivariate analysis between velocity, geostrophic velocity, and density. So it's just a way to improve the cost function, and it can be tested in this context.
Would you? Yeah, my question here would be: would you be interested in participating in this kind of benchmarking experiments?
Yeah, we should see a little bit how with the time schedule of all the works going on. But yeah, I'm interested. I would like. Yeah, I can say yes, totally yes right now. But yeah, would be interesting.
Okay, thanks for this quick feedback. So yeah, probably it's not the time to discuss this specifically, but should be one of the output we should discuss specifically. I think Julien, Emmanuel, and Quentin, Maxime, Mohamed, and I specifically to have more as a final version or first version for this we could propose to SWAT. I see that Julien is in line with this. Emmanuel, probably the same.
Ouais.
OK,
Okay,
merci.
thanks, Quentin. So we may move on to Pierre.
Yes, good morning, everyone. Trying to share my screen. Tac. Can you see something?
Yeah.
Okay. I can start. Yes. So thank you very much, Ronan, for inviting me to this discussion about this work package about the mapping and also the uncertainty of the quantification of uncertainties in data assimilation. So I will talk about that in this presentation. It's a little bit far away from the interpolation of SSH, but there's maybe some links with neural networks. So here I will present something which is quite general in data assimilation, is the estimation of physical parameterization, especially the model, the parameterization inside the models using data assimilation. And here I will present the EM algorithm, which is quite useful to estimate correctly the physical parameterization. So this work has been done with 2 students from the data assimilation course in Brest. This is a quite new course, and I'm a little bit proud of my student because they did a very nice work on that. So this is what I will present today. So just to start, I will take the example of the Lorentz 63 and what are the physical parameters in a model. So here on the right, you have the equation of the Lorentz 63, and you see that the state of the system is x1, x2, x3. So this is a 3-dimensional space of the Lorentz attractor. And then you see that there are some parameters, physical parameters, rho, beta, and sigma parameters. So this is the topic of this talk is to try to estimate those parameters, because most of the time they are unknown in the models. So here in the Lorentz 63 case, the rho and beta parameters that just control the centers of the 2 wings. This is just to remind you what is the effect of these parameters. Very quickly also, I would like to remind you what is data assimilation, what are the equation of data assimilation. So it is based on the model equation here and the observation equation. So data assimilation is just mathematically, it's a mix. We are trying to mix the distribution of a forecast given here, and we try to mix this PDF to this one, which is the observation PDF. And the result of data assimilation is just a weighted mean of this 2 Gaussian PDF. So here I will focus on the I will use the Kelman framework. So I assume that the state of the system is Gaussian. So the forecast and the observation are Gaussian. And also I will focus on the ensemble Kelman filter. So what is the ensemble Kelman filter? It's quite simple. It's at the initial condition, we generate some different forecasts. So we generate an ensemble of forecast, and then we get this covariance, which is PM here. And most of the time we have to a little bit inflate this covariance, because it can be underestimate. So we have to inflate this covariance. So that's why we use an additive term, which is corresponding to the covariance of this error term. And this covariance is Q. Okay. And for the observation, we also have an error, because we assume that there is an error in the observation. So this is represented by this covariance matrix R. So in practice, Q and R are very important in data assimilation, especially in the ensemble Kelman filter and smoother. Okay, so now let's go back to the estimation of the parameters. So you will see that most of the time, the X here, which is what we want to estimate, is most of the time is only the state of the system. So it can be X1, X2, or X3 in the Lorentz 63. But some people try to use what we call the state augmentation strategy to increase the size of the state, and to put the physical parameters sigma, rho, and beta inside the state of the system. Okay, so if you do this kind of state augmentation, so you increase the size of your X variable, and then so you have to specify a covariance, an error covariance matrix, which is now 6x6 matrix, corresponding to different blocks. Okay, so there is a 3x3 block corresponding to the covariance of X1, X2, X3. And there is also a block corresponding to the covariance of the three parameters. And you have the covariance between the parameters and the state of the system. So this is very nice to use state augmentation, because if there is a correlation basically between the state of the system and your parameters, you will be able to estimate the parameters of your model, even if you will never observe those parameters. So this is not new. It has been introduced by Jasvinsky in the linear and Gaussian Kelman filter a long time ago, but it has been applied for the first time in a chaotic system and data assimilation in Annan and Hargreaves. So this is an example of estimation of sigma, beta, and rho for the Lorentz 63, where there are 3 experiments, and they show that this state augmentation is able to converge to the solution. So they decided to take 3 different values for rho, beta, and they show that using different experiments, there is a nice convergence to true parameters. Okay, but what they don't say in this paper, and they don't talk about the initial condition, which is very important here, because here, if you see, they start from reasonable initial condition, not far from the true value of the parameters. And also, they didn't talk about the level of noise they put in the Q matrix, especially the Q matrix corresponding to the parameters. And this is extremely important in the state augmentation, because if you have bad Q matrices for the parameters, it will not be possible to estimate the physical parameters. And this is what my students, Maria and Marceau, they have shown here. So this is a very simple experiment using the Ensemble Kelman smoother, where they start from a very bad initial condition from the 3 parameters of the Lorentz system. So they start from 0, which is very far from the truth, and the truth is here 10, 28, and almost 3 for the parameters. And you see that if you start from the bad initial condition, and if you use a small value, a small perturbation of the physical parameters, you will converge to something which is not realistic. So you converge to the bad parameterization. So this is the first problem when Q is too small. There is another problem if Q is too large. So in that case, you allow the filter to perturbate a lot the physical parameters in your random walk. And this is the result. So you are able to more or less converge to the solution, but there is a very strong variation around the solution, which is better than this part, but it's still a problem because you have a lot of variability around the solution. So here I don't talk about the observation error, which is also very important to tune carefully. So here I just focus on initial condition and the specification of Q, which is the model error. Okay, so so you see that in this experiment, it's just to show you that the estimation of the initial condition and the estimation of the Q is something important that we have to keep in mind. And maybe it can be good to estimate those, I will say, statistical parameters of the filters. So this is what people are trying to do recently in data assimilation. Try to use statistical method to estimate the initial condition, the error of the model, the covariance error of the model, and the covariance error of the observations. And this is exactly what people are doing using a very classical method, which is the expectation maximization algorithm inside data assimilation. So the idea of EM algorithm is try to maximize the likelihood of the observation, and you see that in the state space model, and so this is a model we use in data assimilation. We are able to write the likelihood or the log likelihood, and you see that in this likelihood there are different terms, and there is a x0, which is the mean of the initial condition. P0 is the covariance of the initial condition. And you can also see that Q and R, which are the covariance of the model and of the observation, are also inside this likelihood. And so I will say that mathematically, if you analytically, you will reach to this log likelihood, and then you can derive an estimate of Q and R using the Ensemble Kelman smoother. So the EM algorithm is an iterative procedure where you start from an initial value of theta. So theta for me is where all the statistical parameters of my filters. So the initial condition, the mean and covariance initial condition, and also the covariance of the model error and the observation error. And then, so there are two steps. So the first is to, to apply the Ensemble Kelman smoother with the previous values of the estimated parameters. So the parameter estimated at the previous iteration. And then using these two equation, you are able to update the Q and R matrices and also the initial condition. I don't show this, but it's very simple. It's the initial time of the result of the ensemble Kelman smoother. And you repeat again and again until convergence these two steps. So this is just an example to show you that in data assimilation, the tuning of Q and R is very important. So you see the log likelihood as a function of the error of the model and the error of the observation. And there is a kind of maximum here, and this is what we want to retrieve. So basically, we start from an initial condition. It can be everywhere here, and you will see that it's converging to the solution. Okay, so this yes.
Yeah, we were slightly ahead of time. Could you take 2-3 minutes to?
Yes, I'm just finishing. Okay. There is only one slide. So this is the results when I use the state augmentation and I use the EM algorithm. So this is what my student did, and it's working very efficiently, meaning that. So this is a result at the last iteration of the EM algorithm. You see that the initial condition is very, very well estimated. So the initial condition is very close to the true value of the parameters. And you see here the estimation of the Q matrix corresponding to the physical parameters. So you see that we start from a very large Q, meaning that we don't know, we perturbate a lot the physical parameters. And as long and during the iteration, we start to decrease this covariance because we are going to the solution. So we don't need anymore to increase the covariance corresponding to these parameters. Okay, so this is just to conclude. So so I maybe we'll go directly to the end. And especially, Ronan, you asked me to think about maybe a connection between neural networks and this work and this EM algorithm in data assimilation. So I think maybe there is, so you talk about the 4D-VAR neural network. So maybe this can be in the E steps of the EM algorithm. So you can imagine to take the initial condition and covariance matrices estimated at the previous iteration and use a 4D-VAR neural network in the E steps. And then in the M step, you can update with a very classical equation. So the equation are here. You can update the Q and R matrices. So this can be maybe an option, try to combine EM algorithm and neural networks. Thank you for your attention.
Thanks a lot, Pierre. Are there comments or questions? I don't know if Jung is here. If you'd like.
Maybe I have question.
Yeah.
Yes. Merci. Thank you, Pierre. Very nice presentation. And I was wondering about when you use your expectation maximization algorithm to estimate the parameters of the model. I was wondering about the impact or the influence of estimating the initial condition, because you are still using them to estimate the parameters of the model. So at some point, I think it should converge, no? Even if you are starting from a bad initial condition.
Yes.
Or maybe it can get stuck on a bad minimum. But here they are not using EM.
Yes, here you have an example, for instance, where you start from the bad initial condition and Q is badly calibrated, and you see that you converge to something unrealistic. But what is nice and very efficient in this EM algorithm is that you see here the solution here will be the initial condition of the next iteration.
Yes, yes.
In practice, this is very useful to converge to the solution quickly. So this is a very important point to try to estimate the initial condition inside the EM algorithm.
I'm wondering about this question because I have some, I worked on some similar stuff regarding the estimation of Q and R, and I feel that it's, I will talk about it in 2 minutes, so I will not spoil it.
Okay, good.
But thank you. Yeah.
Thank you.
Thanks, Aid. Maybe Pierre Duong has done some experiments and comparison between EM and other algorithms for the inversions and the estimation of the parameters. That could be interesting to investigate and compare those different settings. The main the difference probably that the dynamic model. Yeah, but including using EM and elbow frameworks, which are also ways to deal with the posterior. So that could be interesting to compare those different settings.
Okay, and when you say Jung was estimating the parameters, you are talking about physical, statistical parameters, or
physical parameters? In the case of Lorentz 63, basically the parameters of the parameterization, the same type of thing. So that could be interesting.
But also, his framework, I think it also includes estimations of QAR, no?
Yeah. I think so.
So this is similar to what I say here, or?
I think from my understanding, I think it's a little bit similar, but he uses EM, and he uses also another way for optimizing, for maximizing the likelihood of the observations, which is based on a lower bound formulation.
Yeah.
Okay.
Okay, thanks. Okay, we may move to say and say you stick on 10 minutes so that we slightly we go up to like 12:15 and keep some time for discussion at the end. Okay.
Yeah. Hi. Share screen. Oh. Yes. It's fine.
Yeah.
Okay, perfect. Hello, everyone. I'm Saeed, and I'm going to talk to you today about some ideas and work we started investigating within people in my team regarding uncertainty quantification for forecast and data assimilation applications of upper ocean dynamics of sea surface dynamics using data-driven approaches. So the general context of this work quickly is modeling ocean surface dynamics, mainly for forecast data assimilation applications. And the reason we want to do that using data-driven approaches is due to the fact that most of the time equations are too complicated or too complicated to be used. And the main issues we have to deal with within this data-driven modeling of ocean surface dynamics is the fact that the dynamics are chaotic, which makes the prior characterization of any data-driven model a little bit complicated, at least more complicated than other dynamical regimes. But another issue is regarding also the observations that are provided in order to do this identification is the fact that they are most of the time partial, and they can be also coming with noise. So given all these considerations, we started investigating on how to assess about the quality of the forecast or the analysis, so the reconstruction of data-driven based framework. So the general kind of framework we are using is a classical state-space model formulation, where we assume that we are provided with some observations, and we want to find something that will propagate these observations in time. Now, when considering ocean surface variables, the observations actually come from a much more higher dimensional state, that is the state of the ocean. And in order to write, can you see my cursor?
Yes.
Perfect. In order to write this model here in space of the observations, we need to make sure that this H satisfies some conditions, which is not the case. So usually what we do is we project our observations into a higher dimensional space, and we do a deterministic forecast in this higher dimensional space. This is a classical framework, and several techniques can be used to do forecast. For example, you can use recurrent neural networks, you can do delay embedding or dynamical embedding, which is a technique we proposed. Now, within this formulation on how to do forecast of partially observed systems or sea surface variables, several ways can be envisaged in order to assess about the quality of the forecast or assess about the uncertainty of the forecast. So we can, for example, instead of using deterministic modeling in this space here, we can use a stochastic formulation of the dynamics that can be useful for forecast and also for data assimilation applications. We need, however, to think about the parameterization of the stochasticity, and most importantly, in my point of view, how to train it, or how, yeah. Another kind of technique is to, this arrow should not be here. It should be on some kind of posterior distribution between this between an irregularly sampled version of X and a reconstruction of U. But basically, we can, for example, use a stochastic formulation of solvers that will optimize a certain reconstruction in order to not get a single mean, but in order to get an ensemble of reconstruction that can be used to assess about the quality of the frameworks. And we'll talk a little bit about this in the end. Another idea now regarding mainly forecast applications is to find a way to randomize the training of this model here in order to get different models that can, with different parameterizations, that will be helpful to assess about the quality of some given framework. Okay. So when considering forecast applications, we had this model we proposed in order to forecast partially observed systems and neural embedding of dynamical systems. And how it works, simply given some observations coming from a higher dimensional space, we project these observations into another higher dimensional space that is parameterized by a differential equation. Now we optimize the parameters of the dynamical equation, so f theta, as well as the initial conditions of the latent states in order to minimize the forecast of the observations. And when optimization is finished, we end up with a geometric reconstruction of the phase space, so something that we want to be diffeomorphic to this space that we do not observe. And we also end up with a dynamical model that can be used to do forecast of the observations, which is very cool. So yeah. We can use such framework, for example, to do forecast, and this is an example of forecasting an EOF component of a patch of the shallow water equation. So in blue here, this blue is the true EOF of the shallow water patch, and the other blue is the forecasted state from this proposed framework. Now, it's a deterministic model, so given an initial condition, we only forecast the same state to infinity. So initially, we don't know how to assess about the quality of this forecast. Is it good? Is it bad? Can we do better? Can we do worse? And actually, what we discovered is if we change the initial conditions of the latent state, so pretty much this noise here, and we train different models. So we train we run this architecture for different initial conditions of the latent state, we actually end up with different models that, given the same initial condition, can forecast our observations differently in time. So using such formulation, we can, for example, pick up, for example, a validation set and specify a prediction time step and predict up to this time step given different models and compute some statistics for the prediction, not to assess about the quality of the forecast of this proposed architecture and not necessarily of one model up to a predefined time step. Yeah, this is what it looks like actually when we go back to a patch domain. It's more talks more to people. So given should run again. Okay, so given the same initial condition, actually what happens is the different models actually simulate their own evolution of the structures. Okay, now from a reconstruction point of view, something interesting about what this proposed model is that if we change the dynamical representation from a nonlinear model to a linear one, we can end up with an approximation, a finite dimensional approximation of the Kelman framework, which is a linear propagator of the observables in time, with observables which are those y's that are solutions of an optimization problem. And linear representations are actually relevant for forecasting various types of dynamical regimes, but most importantly, they allow, in my opinion, they allow us for using extremely simple filtering, Bayesian filtering tools such as the Kelman filter. So in order to do reconstruction using such framework, we implemented this framework, this linear model parameterizing an augmented space of the observations. We wrote it within a Kelman filter in a differentiable framework in order to optimize the parameters of the model as well as the parameters of the filtering scheme. So basically the observation and model error covariances based on a reconstruction cost that includes the sampling of real observations. So what we then figured out is that training the dynamical representation, so basically this matrix, training it based on reconstruction cost is fine. However, training the statistics of the filter, the error statistics of the filter, so the model and covariance errors, based on reconstruction cost is extremely bad, because doing this, we only guarantee, and Pierre will talk to you about this, but we only guarantee a good ratio between the model and the observation error covariances, but we don't get a good estimate of the model and the covariance error, which leads to a good estimate of the mean reconstruction, but to a bad estimation of the posterior distribution. So the uncertainty is completely lost using, for example, training error statistics using a reconstruction cost. So what we did was to include a maximum likelihood criterion in order to optimize the error statistics and still train the parameters of the model using a gradient descent on the reconstruction cost. And how it works, we'll not talk too much about maximum likelihood and expectation maximization. I think Pierre did a very nice introduction about that, but it's pretty much the same thing. So we write the log likelihood of the joint distribution of the states and the observations, and we have a beautiful parameterization of this log likelihood because we are working on state space model, and we go back here, and what we do is simply we train the parameters of the dynamical model here based on reconstruction cost. We end up with an estimate of the analysis that we will use in an algorithm to estimate the statistics, and we do this until convergence. Do I want to say something else? Okay, so we did a toy experiment, kind of a toy experiment on a simple autoregressive model where we assume that we have some observations and we don't know the error statistics, so the 5 and 2 here. And we also don't know the autoregressive coefficient here, the 0.9. We want to train all these parameters using this framework. And it works much better than optimizing everything based on reconstruction cost. So this is actually the thing that I was wondering within Pierre and regarding the initial conditions, and maybe doing another estimation, for example, by changing the initial condition of the Q and R from something that is very bad to something that is closer will help the proposed approach converge more closely to the true covariances. Yeah, so a potential upgrade of this framework that I was thinking about is how to ensure the estimation of time varying covariances and not only constant covariances. So I think that it can be easily done using end-to-end formulation written in a differentiable framework. So for example, if we don't know Q and R, but we think that those covariances vary in time, we can, for example, parameterize them using a neural network, for example, and optimize them to maximize the likelihood of the joint distribution of the state and observations using gradient descent and not using an analytical solution of Q and R, because it will be extremely challenging and almost impossible. This is the first upgrade that I want to work on regarding the application of such framework to more complex data assimilation application. Okay. Now, another thing we have been thinking about within my team is how to, it's mainly my team thinking, not mine, but how to include uncertainty and estimation of the quality of the reconstruction of the 4D VAR formulation that Ono presented earlier. And I think it's extremely important. Such formulation as Ono presented is very advantageous, since it takes full advantage of the sampling of the observations, leading, for example, to results that are extremely relevant when compared to other state-of-the-art techniques. However, it's missing the estimation of the uncertainty. And there is several ways, in our opinion, the opinion of the group, to include an estimation of the uncertainty of such framework. For example, we can, instead of parameterizing, I think Ono talked about this earlier. So phi here is the flow operator, so the integration of a dynamical equation, or just a temporal propagator in time. So if we move phi here from a deterministic model to a stochastic one, we can, for example, estimate the parameters of the model error, as well as other parameters of, and this is actually linked to what Pierre was discussing in his conclusion regarding estimating model and covariance error using EM. So for example, we can do the exact same architecture within parameterized covariances for the model and observation error that can be optimized in an expectation maximization setting to maximize the likelihood of the observations. We can, for example, move to other ideas that I think Juyong investigated the most regarding parameterizing posterior distribution, not necessarily using, but I think that it can be complicated. We can talk about it. Another idea is to, for example, use a stochastic solver. So a quick reminder about what Ono was talking about. So this variational formulation need a solver to minimize the cost of the reconstruction, minimize the loss, maximize the accuracy of the reconstruction. And this solver was actually a neural network model. So if you use, for example, a stochastic neural network solver, we can end up with for the same observations, we can get up different reconstructions, so different analysis, an ensemble of analysis that can be used to compute statistics on this ensemble to assess about the uncertainty of this proposed framework. Now there is this issue of how to sample this noise, how to sample the noise for the solver, and how it interfaces. So this stochastic solver with the old framework that I think need to be investigated. Okay, so that was my 10 minutes. I hope that I was okay with in time, and I will be happy to discuss with you some points regarding what I presented or something else. Thank you.
Thanks, Said. I don't know if there are comments or questions on this. I may start some thought on this. I think it's very important to integrate the uncertainty in those frameworks, and it's not very much done currently. But we have first examples with Stuong and you a bit, Said. That's not it's interesting, but not fully satisfying.
Yes.
To me, there are very classical ways to do this. So basically, we can integrate the stochasticity in the prior or in the solver, or very much the same as what's done in data assimilation usually, or stochastic modeling. Probably something which seems to me slightly different. Here is the ability to learn many different models and learning like ensemble of models, and to use the some kind of uncertainty modeling from very different, many different models and ensemble of models. And probably here, that could be one interest of the learning strategies here, to learn many different models. Could be the same with the same time of hyperparameterization, or could also be with different types of parameterization.
Yeah, I think that it could be interesting, for example, to they can be unified, right? I think that at least for short-term forecast, when we learn all those models, we can do, for example, statistics on the forecast of these models and pick up a mean model and try to include a covariance or a stochastic representation of this mean model that will give us an ensemble of those trajectories. I think that it's a way to assess about the above the uncertainty of this architecture. I think that such representations can be relevant, for example, to assess about the quality of a parameterization. I mean, is a parameterization good or not? For example, the f theta here that was used in this experiment is a linear quadratic model, and I'm kind of satisfied with its results because all of the trained models kind of behave similarly. And if we include the long-term forecast, we can compute statistics on all those models regarding the PSD, the Fourier spectrum, even the temporal one and the spatial one, and it's good in the long term. But for example, if we pick up a bad parameterization of this f theta, all the models will be bad. So we'll have an idea about maybe I should change the parameterization. So it has, I think, several benefits of doing it this way. But what stop me if I'm talking too much. But what intrigues me kind of is why those models are linked to the initial condition on the latent states. So if we get the same, if we put the same initial conditions of on the latent state and we start optimization, we actually get the same models, even if the initial conditions of the model or the initial parameterization of the models is not the same. So what really influences training different model is the initial conditions of the latent state, and this intrigues me. I mean, why does it work that way?
Okay, yeah, but I have no answer on this. But
me neither.
I don't know if others would like to comment this or the ideas in. Yeah, go ahead. I don't know.
Here.
Okay.
Yeah, on this point of the latent initial conditional latent space, isn't it kind of related to the way generative models work with some kind of random noise on a latent variable that you don't control?
I think, yeah. I think also that but you don't control the initial condition, but you you force this noise here, you force it basically to minimize the forecast observations to look like something like this. So it's not what I think is that the first I'm gathering my thoughts. 2 seconds. I mean, this optimization problem is very nasty, right? Because we are optimizing both the parameters of the models and the initial conditions of the latent states. And we can imagine that there is several models that will share the same short-term forecast performance on these observations but they can have different model parameterizations, so f theta, and different initial conditions. And what I think is that the initial steps of training actually condition the whole model. I mean, where do it converge? Because there is lots of local minima, I believe. I don't know if it's clear, but it's feeling that I have.
Well, yeah, for sure, there is not a unique solution.
Of course.
But yeah, maybe a question more to Julien or Emmanuel regarding what could be the most natural way to embed certainty or stochastic features in those models. If you have some insights or comments on this.
I think from a reconstruction perspective or data assimilation, I think the uncertainty should be implemented in order to maximize the likelihood of the observations of the joint observation. But from a forecast, because you will have the uncertainty both of the observations and the model. Now, from a forecast perspective, we have several rooms to take, and for example, we can use this formulation, or it will depend on the model, I think, or in the formulation.
No insight on my side right now.
Okay.
Here, Julian speaking. I need to probably put more thoughts on this. It seems to me that this is really critical to be able to actually have the different visions of the problem converging here and being able to put some representation of the different possible trajectories is certainly something key. But I'm sure that Said, you've put more thoughts than I would have on this. So thanks for sharing it.
Thank you. I mean, just think about it. I'm sure that you will end up with something that I did not thought about. Thank you.
One point here could be to go on discussing those aspects when Emmanuel will start.
Yeah.
Could be and to have some kind of follow-up meeting, maybe more focused specifically on those issues.
Yeah, this is indeed what I was thinking of. I wasn't mentioning, but just for the group to be aware of this. So we have in the room here J. Emmanuel Johnson, who will work in Melody in the Melody project in Grenoble and should start before the summer. Is still in Valencia, Spain, and accepted to join us this morning. So hi, Emmanuel. And indeed, the sort of things that we'll be playing with will be mostly trying to come out with ways to represent the fact and uncertainty in our deep learning based approaches to data assimilation. So that's exactly what you will be working on. So. Indeed, we would probably need to discuss this when you get here to Grenoble. maybe J. Manuel, you could just say a word just to introduce yourself.
Yes, can you hear me?
Yeah.
Yes.
Hello, my name's Emmanuel, as Julian said. Yeah, so mostly the things I work with are kind of more Bayesian-esque type of models. So yes, deep learning, but only with dropout and stochastic outputs and things like that. So these are very straightforward things to do. I also am a fan of Gaussian processes. And as you all know, there's a dichotomy between GPs and stochastic differential equations, as well as Markovian and Kalman filters. So there's definitely a lot of overlap. So I have algorithms in my head, but as we get more kind of, foundationally, we're all on the same page about what you're looking for, what problems you like to solve. I'm sure I'll be able to offer more insight. So I'm looking forward to more discussions like this in the future. Yeah. Hello, everyone.
Okay, thanks, Manu.
Merci.